right. Well, thank you very much for coming to this webinar today. So as Mike said, the topic today is going to be on defect detection and sort of more overall, how do we manage quality control in laser powder bed fusion, and specifically on the Sapphire system that VELO3D makes. So the first main question is, why should we care about defect detection and quality control, and what's the purpose of this Assure software that we have that comes along with our system? And the main answer to that is that even if everything seems to go okay, things can still go wrong during laser powder bed fusion process. It's a complicated welding process, and every effort has been made basically to design the systems as robust and foolproof as possible to make sure that the parts are good at the other end. But that's not all the times possible, and it's very important to be able to identify excursions and quality deviations. So the sort of standard way that can be done, or the way that's done right now in powder bed fusion is you sort of make your parts, and oftentimes you don't find out if there are any critical issues with it until you get to final inspection. Oftentimes done by something like X-ray scans or CT scans. An example of which is shown on the right there. That's a low angle shrouded impaler that we printed with one of our customers. That's showing high quality material on the interior of the part, but you only get that well after the print is done. And so what do you do when you're in a high volume serial manufacturing setting where you're trying to make many parts sequentially? It's not okay basically to find out that a part has gone bad or something in the machine has gone bad, a month after it was printed, because then you might have, a month of WIP in process. Basically everything that was printed from that date, that all might have to be scrapped. And so there's, huge costs and scheduling delays associated with not having good identification of defects earlier on in the process. And so that's a major purpose of what Assure is for on the VELO3D platform. It's to give as early an indication as possible as to whether or not there are any quality control problems. So the other aspect of that is that, one of the major things that's limiting the adoption of laser powder bed fusion parts in end applications is that at the end of the day, industries aren't going to use parts that they don't trust. As great as the capabilities are with additive manufacturing and laser powder bed fusion, as complicated of structures as you can make, and these great new designs that people are coming up with to, push the edge in terms of the performance of individual parts, it doesn't mean anything if you don't have quality and reliability. So if you've got a really awesome part that's got all these cool capabilities, but ultimately they have a really critical, piece on the interior of the part that's really hard to inspect, well, that's going to end up getting designed out, because, all the capability in the world doesn't mean anything if you can't guarantee its quality before you put it, into a critical application. And so without any confidence in the parts, there are no performance gains. So in order for laser powder bed fusion really to push the envelope in terms of performance of the end applications, the quality has to come with it. It's not, it's not an or, it's a requirement. So this is an example on the right there that's showing sort of a layer up build of what a fuel tank that's being built on one of the Sapphire systems. And so, what does quality control mean in AM and in laser powder bed fusion? So, quality control is really critical when you're trying to make that bridge over from prototyping to production. So, in prototyping, when you got, low part numbers and, and oftentimes, there's a certain level of deviation that's sort of, acceptable because they're being used, as test parts or something like that. That's one thing. But in production, you expect every single part that comes off the machine to yield. And so how do you actually track AM quality? Like I said before, it's a welding process. So, in that fuel tank over, that's shown on the right there, that fuel tank is made up of, I think in this case, something like 5,000 layers. On each one of those layers, you're going to have, tens of thousands of laser scan hatches. And then each one of those hatches, you've got billions of events, billions of individual melt pools that are being made. And so how do you keep track of all of that? How do you know that each individual event actually, gave you the quality that you're looking for? And so that sort of gets to what the VELO3D's, platform is, and the fact that we're selling, a full stack solution, we think, to try to address this issue. So there are three main parts of the VELO3D, platform. The first one is the flow software. So that's our preprint software. So that basically is the way the user interfaces with the system in terms of they bring their CAD parts into the, VELO3D's flow software. And this is what allows you to do your build layouts, generate supports on the parts, identify certain surfaces as, needing different processes, do all of basically the build preparation. And then ultimately from that, you get your print file. and you send that to the Sapphire printer, and that's the the printer which actually produces the part. But then a key aspect of that is that that printer or a fleet of printers, if that's how the system is set up, are all connected to our Assure quality validation software. And so this uses a web interface that basically has direct connection to what's going on the machines and can give information about what is the current status of what's going on in the machine. And basically the rest of this talk is to go into what are the capabilities that are in Assure, what is it that you get access to, and how does that ultimately help with the quality validation of the prints that are coming off of the printer. So Assure, we think it provides unprecedented traceability in the market today. So there are three main aspects of what you get out of Assure. So the first aspect is machine health, and I'll talk about that in more detail. But basically, before you start a print, you want to know if your machine is in spec and in calibration, and that there are no deviations. Because if you start a print on a bad machine, you're guaranteed to get a bad part out the other end. So that's sort of step one. Step two is that even if the machine is perfectly healthy, you still care about part integrity. So the machine might be perfectly healthy, but still things might go bad, during the process. And so, Assure gives more indication, not just that the machine was okay, but that actually, the build, went through, under nominal, conditions, and none of the parts were negatively impacted. And the final aspect of it is build reporting. So once you finish the build, you have sort of at that point in time a snapshot of, what was the state of the machine at that point and what happened during that build. And you need some way to basically be able to, transfer that information and have, sort of a traveler or a report that goes along with that build saying, yes, this part was made on a machine that was in specifications and the build was nominal the entire way. So that's where the build reporting comes from. So the ability of the software basically to distill, all of this information down into, something that's reasonable to basically be, a tracker for the part and say, yes, this part was built in conformance. So the first thing that happens when you go into the Assure software is that you get these individual tiles that show you a status report of one of the Sapphire machines that's installed on the fleet. So in this case, this is showing a printer in this called GA16. And so what it shows you is a quick snapshot of what is going on with this printer right now. So one thing you'll see in the upper right-hand corner, there is a little icon, which in this case is green. And that gives you what is the tool health status of that printer at the time. And I'll go into more information in the next few slides about what exactly we mean by tool health. But that's supposed to give a quick snapshot. Green means the tool, is all of the, subsystems basically are in calibration and everything is nominal on the tool and it's ready to print. It's yellow, that means the last time we measured it, everything was nominal, but it has been a certain amount of time since it was last calibrated. And so it's basically indicating to the user that you need to recalibrate the tool to make sure everything is still in spec. And lastly, red. Red indicates there's something that we know wrong with the tool. It's failed one of its subsystem validation checks and it needs intervention. The second thing that you can see on the tile is what is actually going on in the tool right now. What build ID is on there right now? What layer is it at? When is it expected to complete? And then any warnings about consumables on the printer as well, in terms of the tool, the build might be running fine, but there might be a warning indicating that, hey, the recirculation filter is starting to fill up, and you're going to need to hot swap it out potentially before the end of the build to make sure that you don't have a build interruption. And so it gives you a quick snapshot of when you've got a fleet of systems operating at once, tells you what's going on in my fleet right now and what do I need to address right away. So going more into that, more into the tool health and the status icon. So what that is really giving you an indication of is the pre-build system calibration. So there are a number of different, so there's a lot of unique metrology and sensors that are built into the Sapphire system, and they're all sort of designed one way or the other to be able to tell is the machine within spec or not. And so on the print software itself, there's a page for calibrations, and basically there's a series of buttons for all of these different tests that you can run. And basically the operator, if you walk up to the tool, you can just press those individual buttons and it automatically runs through a routine that does a self-calibration of the system. And then the results of which are reported back to Assure. So Assure can say, yes, the system is in spec for these different subroutines, or flag if something is out of spec. And I'll walk through what all of them are in the next slides. So why is all this important? Well, one of the big things for serial production is that having reproducible, characterized processes and predictable, stable production is sort of key to the adoption of powder bed fusion, because the biggest thing that's holding up, and this is a quote from NASA here, is that there's a huge amount of latent risk in trying to use powder bed fusion parts in critical applications, mainly because of the ability to verify individual part integrity. So the inability to be able to identify whether or not machines are healthy and whether or not the builds themselves are healthy is one of the key things that sort of needs to be overcome to get widespread adoption of this technology. So what are the different subroutines? So the first one that I want to talk about is beam stability. And so on the right-hand side of this slide is a schematic of what the laser path looks like on one of Sapphire's printers. So the Sapphire printer we sell now is a 2 laser system. So there are 2 of these paths on each machine. And basically you have your incoming laser, it's going through a focusing lens or a series of focusing lenses, hits the galvo, which is controlling the position of the laser on the actual build plate, and then goes through the chamber window, which is sort of separating the build environment from the optics path itself. Now, one of the really critical aspects of this, or any laser powder bed fusion process, is what is the actual spot size of my laser? So that matters because each of the different processes that you use to make a part can be very sensitive to what is the actual spot size of the laser. So, in many cases, if you're looking to fill a large bulk area of a part very quickly and with high productivity, you're looking to use a really high powered process, and that involves needing to defocus your laser so that you don't get really strong keyholes and sort of get gas processing to break down the process. Well, on the other side of things, if you're looking to do contours or skin processes, oftentimes you're looking to use a very focused beam where you're trying to individually trace out small melt pools that give you the best surface finish as possible. And all of these processes that you're using, they have process windows. They only have, there's only a range of spot sizes in which you're going to get the melt pool characteristics that you're ultimately looking for. Now, one of the problems with these laser systems is that there's an effect that's called thermal lensing, which can strongly impact what goes on in the process. And what this is basically is that on all of these optical elements that the laser is passing through before it gets to the build plate, if there's any contamination on any of those elements, that will cause some level of absorption of the laser light as it passes through that element. And the problem with that is that as you absorb laser light, basically the part or the optical element will start to get hot. When the element gets hot, you get a change in the index of refraction. And when you get a change in the index of refraction, in this case, you get a focusing effect where basically the focal length changes of the optical path. And so what ends up happening is that if you have contamination, say on the focusing lens, as you have the laser on for longer and longer times and that lens starts to heat up, the focal point will start to move on the build plane. And what that means is that you can start, say, nominally with a spot size of, a fully focused beam of 75 microns. And as the laser is on for longer and longer, it can blow up to, 100, 125 microns. And that's basically, you can very quickly drift out of your process window. So one of the things that the system is able to do is it's able to measure this level of contamination. So we explicitly have a subroutine that measures, what is the laser spot size at time equals 0, and then we burn the laser in for a set amount of time at full power, and basically we track how is the spot size changing over that time. And we basically have, very tight controls of this is the allowed change in spot size over that range in time, in which we know that our process window is wide enough that we can handle that level of variation. But if it exceeds that, that is an indication that there's some level of contamination somewhere in the system. And in this case, we can even sort of differentiate, is it likely coming from the chamber window or is it coming from the optics box? And that can trigger, some sort of maintenance action where you're basically going in to clean that level of contamination. But this is, one of those really crucial elements to have before you start to print, because, thermal lensing can really come back to bite the part integrity at the end. The second thing is closely related, is just not just is the focus stable over time, but also is it what you expect it to be when you aim at different parts of the build plate. And so one of the other capabilities on the system is that we have the ability to not just map, what is the spot size directly under the laser normal, for instance, but we also can map it out spatially over the entire build area. So we've got a 315 millimeter build plate, and so we do our standard routine is like a 49-point check basically all over that build area to check to see, when I command 75 microns, am I actually going to get 75 microns at all of these spots? And so this is, one useful when you, first have it set up to make sure that you have really careful calibration of, of the Vario Z position to make sure that when you call, for 75 microns, that is exactly what you get over the entire build area. But also it's very helpful for tracking over time, because you want to know, as things move, as things drift, as there's small changes in the build plane, am I still continuing to get the same, spot size that I'm commanding no matter where I am in the build plate? And so the system has the ability to basically check for that and report that back to the user, what is the variation? And if it's out of spec, we can do a simple, software correction basically to get it back into spec. The next thing to talk about is the complications that come when you go into multi-lasers. So like I said, the Sapphire system, we've got two 1 kilowatt lasers, and they're both have access to the full build plate. And so, the intention basically is that you can make, large parts that fill the entire build area and have both lasers operating on the same part at the same time, and to get the same quality of a part that you would get if you were, producing a part with only one laser. And so one of the key challenges there is the overlay between the lasers. So each path is nominally targeting, a certain position, XY coordinate on the build plate. You want to make sure that, if you command 0, 0 on one laser, that when you command it on the other laser, you end up actually at the exact same position. Because if you don't have that, you can lead to, stitch lines in your part, or, interior defectivity, or, a number of issues if the lasers basically are not well matched. So the system, has sort of two important ways that it handles this thing. So the first one is just the pre-build laser alignment check button. So, with a single click of the button, the laser, both lasers are basically, used at 500 different locations all over the build area to check to see what is the actual position of, one laser versus the other, and then to make a correction to make sure that the two lasers are on top of each other. And so this is, very critical, to make sure that they're well aligned to start with. This is typically something that doesn't change too much over time, but if you have some sort of preventative maintenance, or if the operator had to go in and basically set up the recoder again or something like that, and you get some small change in the build plane, then all of a sudden, the previous calibration might not be accurate anymore. The two lasers might not be pointing in different positions on the build area. So having the ability to sort of easily, quickly, click a button, have it automatically make sure the two lasers are well aligned is super critical for making sure that you get good surface finish, on a single part that's being processed by two lasers, and that you have no issues, with subcontour porosity or anything like that because of an overlay mismatch. So the first aspect is making sure it's good to start. The second complication too is making it sure it's good as you continue to build. And so the system is equipped basically to do this calibration check in situ. So it's not just before the build, it's also happening on every layer of the build. It's checking basically, are the position of the lasers still where I expect them to be, and are they still lined up on top of each other on every single layer? And the reason that this is so necessary is that it's one thing to have the lasers very well matched to each other, before you start the build. But when you actually start the build, you've got a lot of power that's going into the system. That power causes things to start to heat up. The heat causes thermal expansion, and different components in the system will start to move, slightly, but they do start to move. And an example of how that can be so critical for laser overlay is shown here, in these diagrams on the left here. So you can have it where the system was perfectly well calibrated and perfectly aligned, at room temperature before you started the build. But if during the course of the build, some component changed by, temperature of 15 degrees C, for instance, that is going to cause an expansion of the build chamber and a change in the path length of where the lasers, basically how far the lasers have to travel before they hit the part. And that change in path length, combined with the fact that the lasers are coming in at slightly different angles from different positions, means that what originally might have been perfectly well calibrated, you now could have like a 40 micron offset between the two lasers as you're printing. And this is just sort of like a simple example of, the types of things that can cause overlay drift. But in reality, there are a lot of complicated manners in which the two lasers can slightly drift from each other over time. And so what we have is this auto correction capability where, in situ, we automatically are checking, where are the lasers? And so an example of that is shown on the right there. So that's just a really simple test structure of, a block stacked on top of each other. So the bottom is one laser, then switching over to another laser, and then back to the original laser. And this is a system that was, calibrated, had previously been calibrated, in the prior week, and just as printed without the auto correction. One of the faces is still very well aligned, but on the other face, you can see a very clear stitch line where there's, a slight change in the metal position of one laser versus the other. Compare that to, what's on the right there. That's with auto correction automatically on. And you can see now in this case, even when you're switching between lasers, there's no indication of stitch line or any difference showing up. And so, with this auto correction that we have in situ, it's basically allowed us to get to the point where there are no more stitch lines, on our large parts that when you build a single part with 2 lasers, there's basically no difference than when you would run it with only 1 laser. Another, moving away from the laser side of things, there are other important aspects of the machine that you want to be able to check easily before you start a build. One of them is the powder bed itself. So there are multiple different checks here. One of which is being incorporated now. It's just is my recoder set up the way that I expect it to be? What is the roughness? What is the dispense amount, the vacuum amount, all that sort of stuff. But then also, am I getting good gas flow across the powder bed? And specifically, am I having any instances where I'm actually getting powder erosion or deposition off the top of the bed? Because, that doesn't happen normally if this, system's, totally nominal, but, let's say that there was some sort of damage that was made to the gas inlet or something like that. That could cause, unusual flow patterns within the system and could cause, the powder basically to get eroded off the top of the powder bed. So we have a simple routine that we can run before the build starts to basically check, is the powder bed stable over time? And if it isn't, it can escalate to the user that, hey, there's something wrong here. The gas flow doesn't look right. And then, you can take the, proactive steps to address it before you start a build. The last thing I want to get to, and this ends up being very important from when we get to the defect detection side of things, is the thermal sensor alignment. So the system is basically equipped with on-axis detector, where we're looking at the thermal emission of the melt pool in it, that's coming back from where we're firing the laser. So if you look on the left, the main red path, that's the forward path. That's the incoming laser path that's then hitting the build area. But then at that build area, you're making a melt pool, which is could be 1,000 degrees or more, and you're getting a lot of thermal emission from that melt pool. And a lot of that light then is basically traveling back up the same path, and we can pick it off and send it over to a detector. So that's very useful, and it ends up being super critical for the application of defect detection. But one of the really critical things here is how well aligned is your forward and return path, because you want to make sure that that basically what you're measuring is right, is perfectly coaxial with where the forward beam is, because the temperature basically of the melt pool falls off very quickly as you move away from where the laser is. And so if your collection area isn't perfectly centered around where your forward laser is hitting, you're going to get deviations in what kind of signal that you're picking up. And these deviations can then go ahead and turn what normally would be very useful signal, as I'll show in a bit in terms of how it can be used for defect detection, and it can quickly make introduce a level of variation that basically makes those schemes unworkable. So the system basically is equipped again with a simple 1-button click where you check how well or basically what is the offset between my forward path and return path, make sure that they're close enough to each other that we're collecting from the right area, and then we can continue on the build, and then we know that the thermal data that we're going to get out of that build is going to be high quality, and we're still going to be able to get the information we need out of it. So that sort of gets to the tool health characteristics of that. There's also additional information that you get out of Assure related to what's actually going on with the build. So if you click on what's going on the build right now, or you can go back in time and look at the build history of what's printed on that machine before. Each build sort of comes with a simple page that looks like this, where it gives you indications of what was printing, what layers it was, tool serial number, start and end times, information on throughput, on what the consumables were during that thing, and then also were there any interrupts, were there any points during that build where something stopped, and being able to flag those to the user. On top of that, you also get a heat map, which is basically supposed to be a quick snapshot of were the different system parameters in good levels basically throughout the course of the entire build. And I'll go into a little bit what all of these are on the next slides. But the idea here is to give a nice simple visual representation of were things nominal or not. And so the idea is that anything green means that we were that particular sensor was within its specified levels during that particular point of the build. And it's sort of broken down by layers, so you can very quickly see which regions of the build were things nominal and where would you have had issues. And then if you see any that are either yellow or red, you can sort of click on those individual items and sort of drill down more and figure out look into what happened during those layers on that build, what might have been deviating on those levels. So what are these levels? So this is, in terms of what the heat map gives you, this is something that we're sort of, adding to, constantly over time, because there's a lot of information that you get off of the Sapphire printer. There's lots of sensors, but at the moment, the big 5 ones that we check are, one, the peak height, and I'll go into more information on this on the next slides, but the Sapphire system is basically built in with a height mapper, which basically gives you full XYZ information about where all of the metal and powder is on the bed at any given time. And so what we're looking for here is, where is the part relative to the powder that's next to it? One of the reasons that's so critical, on Sapphire printers specifically is, we have the ability to print what we call support free. So basically, we allow the user to print at angles below 45 degrees, down to 0 degrees, without having supports in many cases. So that's sort of like a critical, differentiating aspect of the printer. But one of the things that comes along with that is that the parts will start to protrude out of the powder bed, and some level is acceptable and within tolerance, and some level is not. So we have a non-contact recoder on the system that basically allows for some deviation of the part to move off of the build plane without having any issues. And oftentimes, even when that happens, you have perfectly good quality material. It's just the part is growing at a different level than the rest of the powder bed. But there's a limit to that. If basically the part protrudes too far out of the powder bed, eventually you eat into the tolerance you have between the recoating mechanism, and you can actually have a collision on the part. So what we track is we track peak height, and basically that gives an indication to the user, during this build, what was the highest point of the part, through all the different layers. And then this is the one that's actually, that does have active feedback with the printer, where if it does get beyond a certain threshold, it will automatically stop the printer to make sure that, that you don't get any damage. So that's peak height. The second one is oxygen level, and that's pretty straightforward. It's making sure that the oxygen level is low or within control throughout the entire build, to make sure that you don't have oxidation during your print, and also make sure that your powder is not degrading over time. You have a recirculation filter, so that's, and with respect to the filters that we have on the system that are catching the soot that's being generated. So the system is designed to be hot swappable with its filters. So if you're in the middle of the build and this starts to turn yellow, that's an indication to the operator that it's time to switch the filters, and you can switch from one to the other and make sure that you don't have an interrupt. You've got relative humidity, so that's checking to the water introduction to the system. The water can come in from many different sources, just from opening up the chamber door and having, the air humidity or the ambient humidity get into the system, to, water that might have come in on, the filter media, many different ways that water can get into the system. And this is carefully tracked during the course of the build, because, the water can, do multiple damaging things to the part. One, it can cause oxidation if high enough. And then also, in certain materials, the hydrogen that comes in on the water can also introduce, porosity as well. So it's very important that we have that tracked the whole time. And then the last one is just the remaining powder, so the consumable. So the printer's set up to have enough capacity to be able to make through a full height build with no issues. But, because the powder can be, continuously reused, it's important to be able to, track and alert the user, whether or not this build is at risk of running out of powder, and whether or not you need to do an in-situ powder load to prevent that from happening. The other really critical report that you get from this also is the interrupt report. And so that indicates, did the build stop at any time for any reason? And usually these stops basically then required some sort of user intervention to basically address whatever the emergency was. But you get a clear report of, what were all the interrupts on this build. And so, in this particular case right here, you've got, layer 337, there was a, nearly 4-hour interrupt. And the root cause, if you dig into the reasons there, it turns out to be this was a part protrusion. So in some region, the height mapper saw that the part had protruded, too far away from the powder bed and was at risk for a recoder collision. And so the build automatically stopped itself. And so, this is very helpful information looking back after the fact, when you've got, your part, to check to see, are there any places on the, in the build area or, on the part that you need to have special attention to, because there could have been an interrupt for some reason. Like I said before, there's a height mapper system built into the Sapphire printer. And so this is sort of this unique capability that allows us to get full XYZ information about where is all of the powder and where is all the part material, over the powder bed in terms of how high it is relative to nearby powder. We the system is designed to take these images, 2 times, once after the recoat itself, to make sure that, the recoat quality was good and there weren't any issues when we were laying down the next layer of powder. And then again, after we finish lasing the bed, to basically check for, where is the metal now that I finished lasing, and do you have any indications of part protrusions? And so a good example of that is shown, on this slide here, where this is a part, on the right hand, or the part on the right is some sort of shrouded impeller. On the left, it's I think it's a toy part of some sort. And on this layer, on the left hand side of the slide, basically everything was nominal. So you finish lasing the part, and you can see that there's some deviations of where the part is relative to the nearby powder, but it's all sort of within expected levels. And then you look over on the right hand side, you can see a case of where that's not the case. Where now you've got certain regions of the part has actually protruded significantly from the powder bed. And I think in this case, this was due to a strategy that led to some sort of crack in the part or something like that. But the height mapper basically gives you this information on every single layer, where is the part relative to the powder bed, and that can be useful for, one, looking for, catastrophic interrupts where the part literally failed. But even for doing, more in-depth analysis after the fact, you can extract a lot of information about about what happened during the build from just looking at where the metal was. Lastly, all of this information, and there's a lot of it, and we have the ability to distill it down into sort of a simple build report. So to consolidate all of that sensor data that was picked up during the build, all of the tool health characteristics, what was the calibration status of the tool at that moment in time when that build was run. And we distill that down into, a simple PDF report, which then can act as like a traveler to go with the part that can indicate, this part was not only built and spec the entire time. So that covers, the tool health and the machine health. But now, there's another level beyond that, which is important, which is, even if the tool was completely healthy when I started the build, and even if there were no interrupts during the build necessarily, that's necessary, but not necessarily sufficient to tell you that the part is defect free. And so we spent a lot of time at VELO and working with the Assure software and with our algorithms and things like that to basically try to tease out additional information to identify, were there any areas on the build that are likely to have defects. This ends up being a really complicated effort. And I know that there are a lot of people, sort of throughout, competitors and industry and academia, all, trying to tackle this very problem. And what it boils down to is this. There's a lot of data that you get out of the builds. Like I said, there are billions of events. You've got many thousands of layers and many hatch events that are happening on each one of those layers. You get a ton of data, and you get a lot of signal out of that data. So in our case, we're focusing, in what I'm going to talk about right now, we're focusing mainly on melt pool emission data. But there's other sensors on the system too that you can extract data from. But especially in terms of melt pool emission, a lot of that is driven by variables that are unrelated to defect generation. So there's a lot of systematic reasons that the amount of light that you're going to collect out of a hot melt pool will be different, even if the melt pool itself is not necessarily any different. So just collecting that data by itself is nice, and you can make some cool plots out of it, and in so many of the extreme cases you can tell what's going on. But ultimately, it's sort of too dense, and you need to be able to, from all of that data, be able to extract out important signals that can actually be acted upon by the users. And so we spent a lot of time working on specific algorithms to basically try to separate the signal from the noise, try to tease out, and remove all of the, systematic variation in melt pool emission, and extract really what we care about, which is, are we making a defect or not? And there are two different aspects I'm going to talk about here. The first one I'm going to talk about is surface defectivity. And so in this case, I'll show like a couple examples of basically how this was, built up, how well it works, and then, its application to larger parts. So one of the things we're trying to do is we're trying to predict, is the surface going to be defective or not? Am I going to have any high roughness on the bottom surfaces, especially? And we call them, in these cases, we frequently refer to them as melt pool instabilities, because it usually indicates that, especially when you're doing a low angle surface, if your melt pool is not carefully controlled, you can have, the melt pool basically break apart instead of, solidifying in into a nice ball. And that leads to, surface defectivity and roughness that's on the surface. And so we're trying to, use the data that we have during the builds to predict when this is happening. So in this case, we've got a, simple test structure showing, a low angle cone that's basically growing out. I think it's at 15 degrees in this case. And we're trying to say, based on the sensor data, can we predict whether or not the bottom of the surface is going to be defective or And this is an example of the defectivity algorithm that we've created and how it works on these types of test structures. And you can see on the right-hand side, that's a key and surface profile of what the bottom surface of that part looks like. And the areas in yellow, sort of near the top of the part, those are protrusions. So those are basically areas of very high roughness where you had these melt pool instabilities, where you had a breakdown, and then you ended up with high level of surface roughness. On the left, you can see where the algorithm has predicted that there is going to be defectivity, with each of those individual red points indicating that that is that's a melt pool instability. That's where we think the melt pool broke apart, and that we ended up with this surface roughness. And you can see when you compare the image on the left and the image on the right, there's very good correlation between the two in terms of spatially identifying where am I likely to have surface breakdowns. The nice thing about this algorithm too is that it's quantitative. So this is just an example here of an experiment that we did where we had poor process engineer had to go through and he had to count each individual melt pool instability that he saw on the part, and then we compared that to what the predicted defects were for those same parts, and we can see that there's a very nice linear correlation between when we see a defect, the algorithm also picks up that there is a defect. Now, one of the most exciting things about this algorithm is signal to noise. So with the approach that we've taken here, it turns out we can get very good signal to noise for this type of defect mechanism. And what that means is that it's one thing for something to work on a test structure, but even when we go to actual real parts with more complex geometries, the defect detection still works. So in this case, on the right-hand side, I'm showing two low-angle shrouded impellers. So I think in these cases, these impellers go down to like 3 degrees near the outer radius. And so we basically built these shrouded impellers, and then for the sake of testing, we cut them in half and flipped them over, and we looked at on the underside of the shroud where we were growing at low angles, what does that surface quality look like there, and what does the algorithm tell us in terms of what the surface quality is. And you can see when you compare the parts on the top versus the predictions on the bottom, again, you're getting good correlation between where the algorithm is detecting that there are surface instabilities and defects and where there actually are on the parts. And there are two really great things about this. One is that this all happens in real time. So while the build is going on, you can get information of, on that given layer, am I likely generating defects or not? And, so that means that you don't have to wait until you get to the end of the part to know that you've got a problem. And, maybe at that point, there's something you can do about it, change the geometry, change the strategy, maybe there's something wrong with the tool that you need to check on, make sure that, everything's in spec before continuing to build. The second aspect of this really important too is, because of the flexibility of, AM in general, but also the support-free functionality that VELO has generated is, it's possible to make very complicated geometries, especially with inaccessible internal features. In the simplest case here is just, this type of shrouded impeller, which, is a very common type of application, but at the end of the day, it's got these internal channels that many times are difficult to inspect. And so because you have this algorithm that can basically parse out whether or not you got defects on the skins or not, you can easily identify if you've got any issues on any of these internal channels, without having to, destructively tear the part apart and check those individual areas. And so it's very beneficial in these cases where you've got these complex geometries, which are otherwise challenging to inspect. Now, this is an example of a good case, of a case where we've got a test build where nothing interesting happened. But on the right-hand side there, you can see the actual part. It's the fuel tank that was shown earlier on. And in this case, you can see, this is the type of part that would be very challenging to inspect because, basically all of the low-hanging surfaces, especially up near the top of the fuel tank, it's very enclosed. And so if you want to inspect it non-destructively, you sort of have to sneak a borescope in there or something like that to try to inspect those surfaces. But with our defect detection algorithm, we can basically tell you, based on those plots on the left, that there are no defects on the interior of that. And so in this case, we cut the part in half and we looked, and sure enough, there are no defects on the interior of that. So it gives you lots of, good information about what's going on my interior surfaces without having to do destructive testing. So the last thing I want to talk about is bulk core defectivity. So we've talked in the last few slides about what we're doing on skin defectivity and surface roughness and breakdowns. What can we do also to tell us information about what's going on in the interior part? Because that is also oftentimes that's what's dictating the ultimate strength of whatever the part is being made. So we do have a bulk defectivity metric that we track that has over layer, and this is just indication, a picture of what Assure is showing for a typical build, showing this defectivity metric as a function of layer for the two different lasers. And so what this defectivity metric is an algorithm that we developed to basically try to extract what do we think the volume porosity is of the core based off of these signals. And so we did a sort of exhaustive study of this with Stratasys Direct Manufacturing about a year ago, and there's a white paper that's been recorded about this. But the gist of it is that we do see with this algorithm, we can get a pretty decent correlation between the volume porosity of the part and this defectivity prediction thing that we're getting. So if you look on the right-hand side there, that's basically all the data that was collected in the study, and it's a combination of many things. One is everything that's in open triangles or circles or squares. That's all nominally production data where there was no intentional defect added to the build, so that's just nominally running the same part over and over again. And then in the filled triangles and circles, that's places where we basically intentionally introduced the defect into the part. And in this case, we tried to do it in somewhat in ways that would mimic real world failures. So in one case, we did it by intentionally dropping the gas flow, so we would build up condensate within the build and introduce defectivity that way. And then the second way was by introducing defectivity by through the recoder. And in both cases, you can see that there's a decent correlation where you can see that as the volume porosity of the part goes up because you've intentionally added these defects, this metric also goes up at the same time. And so there's, to sort of first order, you get a reasonable correlation. The challenge here, though, is comes back to signal to noise. So in the case of the skin defectivity, we have good enough signal to noise that we're pretty confident that when we see something, we know it's an actual defect. This one's a little bit trickier because there's a fairly wide range, which is sort of indicated in yellow there, of where we have a range of values that are coming out of our algorithm, and about an order of magnitude difference in defectivity for those different parts. And so that's really something that we continue to focus on, is to continue to try to improve this algorithm and further tease out the actual signal from the noise. So what we can say right now is that for test parts and when you've got large deviations, the algorithm works okay in terms of identifying whether or not you've got a major excursion. But in order for it to really be more valuable going forward, this is something that we continue to invest to try to further reduce, improve the signal to noise, to try to tease out smaller and smaller deviations and give that much more feedback to the end customer about the level of defects in the part. So in summary, like we said from the beginning, industries aren't going to use parts that they don't trust. We need quality control mechanisms in place for all of these parts that we're making, and there's a ton of information that is coming off of the printer that we can leverage to try to provide more and more confidence in the quality of the part that we're making. So Assure, as we've built it now, provides unprecedented traceability in the fact that we've got integrated machine health routines basically that track to make sure that the machine is healthy before you start a build. We've got information on the part integrity when you're actually going during the build. And then we've got this build report as well that allows you to basically generate a status report of what happened during the course of that build. And now as we move forward, Assure is getting even better with our introduction of defect detection modes. And so, at the moment, I would say that our skin defect detection is quite robust for complex geometries and for downskin processing complex geometries. And so we can really leverage it for internal channels to look for breakdowns and defectivity. Our bulk defect detection is still more of a work in progress. It can work on test geometries with large deviations, but really, like I said, it's all about further teasing out the signal from the noise and trying to improve these going forward. And so that's an active area that we're investing in going forward. And that's all I have for today. So open for any questions.
Great, thanks, Greg. We have a lot of questions here, so we're just going to start diving into it and work our way through. As a reminder, if you do have a question, please post it in the Q&A channel. I've got that open in front of me, and I'm working my way through it. Any logistics items, I'll try and type an answer to. Anything best left for Greg, we'll ask him live. Okay, so let's kick it off. This one we get a lot, but how does the recoder work if it doesn't contact the powder bed? We'll start there.
Yeah, so it's a non-contact recoder, and so effectively the way it works is that we on a typical build, every layer has 50 microns of powder, or that's the elevator. That's how much we drop the elevator on it for every single layer. So you're trying to lay down 50 microns of uniform powder on every single build. The way that we work with the non-contact recoater is we basically have a mechanism that allows us to deposit an excess of powder, which we then can cut smooth. And then we can, in a non-contact mechanism, basically remove the powder down to that 50 micron level. And that clearance basically between the cutting level and what you've removed the powder down to, that is your clearance that you have for the part to protrude from the powder. And so that's what gives us the ability to allow the part to protrude slightly from the powder as you're building it without having to stop the build.
Kind of dovetailing into that, you showed a slide where there's a warning for 400 microns of height. And I think maybe there's some confusion on what that metric is showing, because the next question is, what's the full layer build of the height? Or how many layers are in a build? So maybe you could describe on what that metric, when you say 400 microns in height for a warning, what is that referring to?
Yeah, sure. So on every layer, you're getting, what is the, you get all the points of the metal, but you also are getting this one metric of what is the highest point of the metal relative to the nearby powder. And so, like I said before, there's a certain amount of clearance that you have from the recoating mechanism to the actual build plane. Now that can be adjustable depending on exactly how the system's set up, but roughly it's on the order of about 1 millimeter. So the part can protrude about 1 millimeter before it would actually contact anything. And so we'd have different thresholds that basically give, the first one is a warning threshold, which alerts the user that, hey, the part is now 400 microns above the nearby powder, and so that's an indication, that that's just happening, and also that potentially that there's something going on with that particular build, and can give the user the opportunity to fix it. And then there's an emergency level, which then triggers, I think currently at about 850 microns, which basically says once the part actually gets above 850 microns from the bit, that's actually the point where the machine will stop itself to make sure that we don't collide with the recoating mechanism. And so there's all that, that area in between is basically fair game. Anywhere from 0 to 850 is how much the part can be protruding, and the build can continue to go. And like I said just earlier, the actual step size during the build is 50 microns typically. And so we're, that's how much we drop the elevator by each layer. But, like I said, when you're growing support free and we're growing at these really low angles, each layer might only be 50 microns thick, but the actual position of the metal in the part while you're printing it may be, different from each other by, hundreds of microns.
Okay, so it sounds like it's measuring the difference between the powder or the target powder bed height and anything that would be protruding above that, not necessarily the build plate in the part. Yes, that's correct. Okay, yeah, it seemed like that was what he was asking. And then a follow on to that is, how does the height mapper determine the distance that the part's protruding? Basically the height mapper it was homegrown or home developed at VELO to basically be able to capture the Z height information using techniques that are kind of out there in terms of how you can do it. But what we end up getting is XY resolution on the order of about 100 microns, but the Z resolution is very accurate, so it can be on the micron level. And that's how we can determine exactly where the part is relative to the nearby powder bed. It does it says heat map, but I think they mean height. Does the height mapper map each part, even if they're if they're nested on top of each other, or does it only work for one part at a time?
So it works on a layer level. So basically, after every layer that you printed, it gives you the XYZ information for that particular layer. So if you've got in your build volume, if you've got different parts stacked on top of each other, it'll collect all of that information, but it works basically at the layer that you're printing at that moment in time. So after the fact, you could then reconstruct where is the part throughout the course of the entire build. But the main point of it is to give you a 3D map basically on every single layer of at that point in time, where is the metal relative to the powder.
Why can't the protrusions be avoided by using parameters, for example, process parameters?
Yeah, that's, there's been a lot of work done on that, and, to enable, us to be able to do support free. So, in most cases, there aren't large protrusions. But, that said, no parameter set is perfect, and and it's always possible to come up with a geometry that's, more impossible than the last. So it is still possible for you to get protrusions that, are large enough that they can hit the recoder. And then sometimes also there's just, simple, mistakes in terms of the build preparation, large free floating surfaces that, aren't adhered to anything that just, instantaneously appear, at a certain Z height. We haven't figured out how to print everything yet. So, if you try to print a gigantic, square sheet that's completely unsupported all on one layer, that is going to warp up. And, to our knowledge, we don't know of any parameters that will prevent that from actually happening. So there are still cases that you're going to get into where the part will protrude.
Does the height mapper know the difference between a part and powder? For example, if you have a mound of powder versus a protruding part, would it know the difference between the two?
Yeah, that's an interesting point. Not the way it's implemented right now, but there is additional information that you can get that can help differentiate the two. So it just sees height one way or the other, but like in terms of the contrast, there's oftentimes a very large contrast difference between what is glazed metal and what is powder. And so from that, you can extract more information in terms of whether or not the protrusion is powder versus the part. So that's definitely possible, and I'm sure that'll sort of work its way into Assure in the future. But at the moment, it just gives you the height.
Okay. Is there a method to use the information from Assure in a closed loop format to fix the defect while it's printing?
So that's an interesting question, and basically the printer has a lot of those capabilities built into it. So for instance, in the low angle skin defect detection, we're getting thermal emission data from the mill pool itself. The system is designed that it can run in closed loop control, where it can basically then modulate the laser parameters to try to control that signal. At the moment, we don't operate with any of that on, mainly because it's very complicated when you start to introduce the closed loop feedback, and it requires a large level of confidence in exactly what you're measuring to make sure that you're doing something helpful. And we found that for many customers, having the build file be completely predeterministic and sort of locked in when you load it on the machine is much preferable from a qualification standpoint than trying to do any closed loop correction. So while the system is built that it could do that things, currently a lot of that functionality is disabled. The only, there are a couple of small cases where that's not necessarily true. So there is a feature on the tool where if it detects a streak, in the powder bed, after you do the recoat and if you see an individual streak, sometimes that's caused by something that can get fixed easily in situ by basically doing a retry. And so the system can be enabled to basically, if it detects that a streak was made, it'll automatically try to repair that defect so that you don't end up scrapping the build. But that's sort of that's the kind of level that it operates under right now. We don't really try to detect them apart when we see them.
And if you do detect a protrusion that's below the warning level, what does the machine do? Does it just ignore it and keep printing, or does it compensate to fix it?
No, there's no compensation scheme. It's extremely helpful information to have after the fact when figuring out how potentially to design a part better, or for helping to compare. You printed the same part two times and you're trying to compare exactly what happened on the two builds and make sure that it was the same. But basically, all of the information below the emergency threshold is just that. It's just information provided to the user. The machine only does something if you actually hit the emergency level.
We've had two on this, and I'll go ahead and cover it. We are recording this session today, and we will make it available on the VELO3D blog page. So go look at our blog page. On Monday, we'll probably have it posted. So I do see a couple questions on that. All right, back to this. Is there any way that customers could have under the hood access to some of these algorithms or some of the data to improve their own part development?
There's definitely a lot of things that are on the roadmap for how we're going to further improve Assure going forward. So one of the things that is definitely on there is more direct access to the actual raw data that's coming off of the system in terms of exactly what the thermal sensor data looks like, and that is currently being worked on. Sort of the software team is working on this API, which basically will allow access to the end user of this information. So if the end user wants to work on developing their own algorithms or use the information in some other way, they will have the ability to do that. So we sort of have our layer on top of these are algorithms we've come up with, and this is what we think is useful. But we're planning on opening up that to allow people to develop on their own, basically their own quality control metrics.
Okay. How is the thermal sensor data, just moving away from defect or protrusions here for a second, how is the thermal sensor data visualized and analyzed to see the defects? And I think you showed some of that earlier.
Yeah, so the way it works right now is that, so there's a lot of data that you're getting because, it's being captured at very high frequency. So it doesn't necessarily make sense to just, dump out, here's exactly the number of photons that we were reading at every single point through the course of the build, because then, it's kind of overwhelming. It's hard to tell, what it is you're looking at that point. So the way it works right now for the skin detection algorithm, at least, is that, at a particular region on the part, basically what it does is it ends up outputting a XY coordinate in a layer position, and then a flag, basically 0 or 1, as to whether or not we expect that there's a defect or whether or not we think it's okay. And so then you get you can then export that if you want as like a large a table, basically, to identify where on the part you expect the defects to be. But it's distilled down from the raw data, so you're not getting the super high frequency sampled data in that case. You're just getting something more manageable, which is XYZ location and whether or not there is or is not a defect.
Is this information unique to VELO, or do other companies provide this information as well? And I guess I'd ask that broadly, and I know some is and some isn't, but maybe you could describe some of the things that are unique.
So that's a good question, and it's changing quickly, I think, across the industry. So there's a lot of new functionality that's being brought onto these printers at any given time. So it's hard for me to keep up exactly with what is completely unique to us and what isn't. I will say, though, I think the height mapper and the whole XYZ capabilities and the mapping of that on every single layer, I believe, is unique, and also so is the skin defectivity algorithms. I couldn't speak to necessarily all of the other aspects of it in terms of what happened during the build and interrupt reporter. I imagine that there are other systems out there that offer that. Another thing that is unique, though, I think the one button click tool health calibrations is a unique thing on the VELO Sapphire system. So our ability to measure thermal lensing and spot size and stuff, have the tool basically measure itself and then report on its status, I believe that is unique.
There's another question. So perhaps I'm missing something, but how can this system tolerate a 850 micron protrusion from the layer? So a little bit about the non-contact recoder that you were talking about.
Yeah, so basically the recoding mechanism, it's not a simple sort of doctor plate method that's used on many other printers. So there's basically a plane in which the recorder is moving across where it's cutting the powder. But that plane is a full millimeter away from where you're actually building the part. And so what our recorder does uniquely is that we have a way basically to, without having to touch the part, we can remove the extra 950 microns from the cut surface down to where the part is in a non-contact way, such that there is no physical interference between the recoding mechanism and the part. And so that means that the part, it can continue to protrude out of the powder bed throughout that range without actually hitting anything on the build, which means the build can keep processing.
This one's about bulk defect detection, and the question is, how well does the current system catch porosity? Any data on detection rate or false positive rate?
Yeah, so that's a good point. So the last slide I had was sort of getting to that, and sort of where it is right now is for a given test part, in the case where you have a large scale deviation, it's pretty good at detecting that there's been a deviation. But there is a fairly wide range where you have more subtle deviations, where the false positive rates is much more problematic. And so in those cases, you can have 50% false positives or something like that. So sort of where it is right now is it all comes down to the signal noise. If you have a large enough deviation, you have enough signal to basically break out of that noise and get, a robust defect detection. But in that intermediate range, it's just basically the signal noise is too small.
Okay. There's some questions here, actually a couple of them. If a protrusion is detected requires human intervention, how likely is it that the build can be recovered? I've actually seen a couple on that.
Yeah, so I think that really depends on what the application is. So it's really useful for especially development builds where, the user is basically trying to push the machine to the absolute limits. And then also, in the case of, supporting strategy, oftentimes in terms of saving, time and cost and quality on the end part, they're trying to remove get rid of every support that they can in the print itself. And so in those cases, it can be really useful because you can basically try something very aggressive and the machine will basically stop itself before it starts. And then you can, the user can then, anything from, start the build over, remove that particular risky part from the file and keep going. Or, we've even seen in some cases, the user literally opens up the machine and hammers version and then keeps going, because if it's a development build, you're trying to push the system to the limits and see what you can get away with. But I would say like in a production setting where you've got, a part that, that's already gone through that, development part, development work, and basically this is the thing that you're just trying to make serially, there basically should be no protrusions that trip the threshold. And so, if you did end up getting a protrusion that tripped the threshold, that would basically be a scrap part.
How often does the Sapphire have its own calibration system recalibrated?
How often does it have? So for in these different cases, we have other basically there are other instruments that you can bring over to the tool. Especially in the case of like thermal lensing or something like that. We have a tool where you can basically stick a CCD camera into the tool and basically measure on an actual camera how the spot size is changing over time. We found that these metrics though are pretty robust and oftentimes even easier or more accurate to use than some of the other methods, and so they don't need to be recalibrated. Pretty much, we basically don't need to recalibrate them. They work very well on their own, as long as all of the components of the system are in spec. Especially a big one there is the thermal detection. So like I said before, making sure that the forward path is well aligned with the reverse path, that's critical for having a lot of these system calibrations working properly. And so if that is in spec, oftentimes it usually means that the one button click calibration is also going to work properly.
And how often would you recommend to run the calibration routines, the regular ones?
So at the moment, I think the defaults in Assure is that it automatically switches everything to a warning after it's either 1 week or 2 weeks, where it basically gives you a warning that you haven't run the calibration recently enough. But a lot of that comes down to customer preferences and where they are in the life cycle of whatever it is that they're making. So for many customers, they'll run laser alignments after every single build. Especially, since it's fairly easy to do and it's, you click a button and, you walk away and 20 minutes later, the system's done. It doesn't add that much time. And so, for some customers like that's the level of risk that they want to take. Because the way we envision this working is that, if something on the tool is found to be out of spec, then that basically makes everything that's been printed from that date to the, last date of good calibration suspect, and then you have to sort of quarantine it and disposition it and potentially scrap the whole thing. So a lot of it depends on what's the tolerance for that. So in many cases it just makes sense to run the tool calibrations before every build to avoid that situation.
So I just checked the time. We're actually about 7 or 8 minutes over our projected time, but one last question for you. How can people get in touch with you if they have future questions or want to learn more?
Yeah, sure. So it's easy to contact me through my email. It's gregory@velo3d.com. Or you can reach out to Mike, and I'm happy to answer any other questions.
All right. Thank you very much. And any final words before we close today?
Nope. Thanks all for your attention, and appreciate the time.
Yeah. Thank you, everyone, and have a great week, and have a great weekend.